Good day, ma'am. I am Angelheart Trinidad, BSME first year student and in WSECU. My presentation is all about quantitative analysis of fluorine nanomaterials and environmental system. Without any further introduction, let's move on to the objective of this study. The central objective of this presentation are to provide the reader and the listener with a report of the state-of-the-art analytical methods for quantifying fluorine nanomaterials. Second, a discussion of how improvements in analytical methodologies will play an essential role in advancing our understanding of fluorine nanomaterials, occurrence, fate, transport, and biological effect. So for the main topic of this presentation, it is fluorine analysis state of the art and fluorine occurrence, fate, transport, and effect. The subtopic of fluorine analysis is extraction, separation, and detection. For the fluorine is occurrence, fate, transport, and biological effects. So, a fluorine is an allotrope of carbon whose molecule consists of carbon atoms connected by single and double bonds so as to form a closed or partially closed mesh with fused rings of 5 to 7 atoms. The molecule may be a hollow sphere, ellipsoid, tube, or many other shapes and sizes. Because fluorine takes a shape similar to a soccer ball or a geodesic dome, it is sometimes referred to a buckyball after the inventor of the geodesic dome, Buckminster Fuller, for whom the fluorine is more formally named. Fluorine and surface functionalized fluorine classes of nanomaterials are proposed in optical, electronic, cosmetic, and biomedical applications. The potential toxicity of fluorines, fluorols, and fluorine derivatives is an intensely debated issue. For example, there are reports that pristine fluorine are non-toxic and the fluorine water system has a wide spectrum of positive and unique biological activity. That antioxidant effect of water-soluble fluorines is Cabejan's reactive oxidation species in human skin cells, and that fluorine is powerful antioxidant with no acute or subacute toxicity. So for the main topic, fluorine analysis of the art. This section presents the current state of the art analytical methods that are commonly used for analysis of fluorine and surface functionalized fluorines, with a focus on complex environmental matrices. Methods that offer information on fluorine only as particles, such as aggregate, size and mobility, including transmission electron microscopy, quartz crystal microbalance, X-ray photon spectroscopy, light scattering, and electrophonic mobility are reviewed elsewhere and not discussed further. Extraction. Methods for the extraction of fluorines from environmental solids, including sediments and combustion-derived salts, currently consist of sonication or succinylate extraction with toluene. When extracting 60 atoms of carbon and 70 atoms of carbon fluorines from carbon soot using supercritical carbon oxygen 2, modified with toluene. In contrast, water-stable carbon atoms, 60 atoms of carbon are not efficiently recovered from aqueous solution using toluene alone due to their polar nature. Alternatives include toluene with a required addition of salt, evaporation to dryness, and solid phase extraction. Separation. Differentiating between various fluorine forms is accomplished in part through chromatographic separation. To date, the emphasis is on 60 atoms of carbon, with a few reports indicating the chromatographic separation of 60 atoms of carbon from 70 atoms of carbon. The feasibility of identifying and separating a wide range of fluorines is indicated by Isaacson et al. The most frequently reported separation condition of fluorines and hydrophobic surface functionalized fluorines and based on reverse phase columns such as 18 atoms of carbon and mobile phases containing toluene and methanol. acetonitril acetone isopropanol or THF, serving as the polar mobile phase component. Fullerene retention on 18 atoms of carbon columns is achieved by adding a polar solvent to the injection solvent, and elution is achieved by increasing the percent of the non-polar solvent, typically toluene. Detection. Currently applied analytical methodologies with the ability to differentiate the various molecular forms of fullerenes, including liquid chromatography with ultraviolet detection and 13 carbon in MR. However, mass selective detection offers advantage of selectivity when compared to the aforementioned approaches. Mass spectrometry offers the capability to distinguish fullerenes based on their molecular weight. So finally, quantitative methods that are applied to geological, biological, or aqueous matrices for which one or more performance parameters such as accuracy, precision, and detection or quantification limits are presented are described in more detail. So let's move on to the second main topics: fullerene occurrence, fate, transport, and effects. Presented in this section is the critical role analytical chemistry will play in determining the occurrence, fate, and transport and biological effects of fullerene nanomaterials. Methods for determining the occurrence of fullerene in environmental solid must be optimized to fully understand environmental fullerene distribution. The fate of fullerene is in environmental and engineer system is just beginning to be explored, and methods must be developed to determine the identity, transport, and effect of transformation products. Finally, reports on the transport and effects of fullerene nanomaterials are discussed. Occurrence. I will not just read the written in the screen, but I'd rather explain it. To the best of our knowledge, there are no data or naturally occurring fullerenes in biodata or water from a natural or engineered system. However, it is anticipated that the number of reports will increase significantly as the methods are used, modified, and demonstrated for the purpose of describing the occurrence, concentration, and range of the fullerene forms present in surface, water, grounds, and wastewater. Due to the shortage of time, I will move on to the conclusion of this study. Fullerene nanomaterials may therefore deceive the application of any single analytical method that is applied with the assumption that fullerenes have but one defining characteristic. First, I find that analytical procedures are needed to account for the potential transitory nature of fullerenes in natural environment through the use of approaches that provide chemical explicit information including molecular weight and the number and identity of surface functional groups. Second, I suggest that sensitive and mass selective detection, such as that offered by mass spectrometry when combined with optimized extraction procedures, offers the greatest potential to achieve this goal. With this review, I showed that significant improvements in analytical rigor would result for an increased availability of well-characterized authentic standards, reference materials, and isotopically labeled internal standard. Finally, the benefits of quantitative and validated analytical methods for advancing the knowledge on fullerene occurrence, fate, and behavior are indicated. I conclude that the full exploration of the mechanism behind fullerene toxicity in terrestrial environments clearly requires information about the molecular properties of fullerenes that matricize up aggregate. This emphasize the necessity for analytical protocols that are able to provide chemically explicit information, including molecular weight and number and the identity activity of surface functional groups. Thank you for listening, and God bless.